So, hello everyone, I'm André Juan from Brazil, and I'm going to present problem number 6, sonic black hole. So before we talk about this problem, before we go sonic, let's first take a look on regular black holes, the standard black holes. Of course, they are a theoretical emergence for general relativity, a theory for gravity which is purely geometrical. This is the main point here. General relativity comes all about geometry. We treat space-time not as something fixed, but as something geometric which is curved, and curvature here is very important. We have here our Einstein field equations, which this here is our solution. This is our what we seek, and this is the metric tensor, its components actually, which actually describes all we can get from the space-time geometry, which is mathematically modeled as a manifold, technically speaking. So the thing is, this equation gives us the structure of space-time. And of course, if we solve the equation, we have this as solution, the metric tensor itself expanded on its basis. And, well, it's just geometry, of course. This is a solution which describes the exterior of a given mass distribution, the vacuum outside the star, for instance. But you could say, okay, this is geometry, you have some mass here, but where's the black hole? So, if we look here in this term, you see this related to radials, to the radial component of our metric, of our geometry, so to speak. If we put this value here exactly in our radius, it goes to 0, under 0, 1 over 0, so we have infinities. And infinity physics are always trouble. So this is where we have our problem. This is where our black hole emerges. We have the event horizon, which is the surface in this exact radius value from which nothing can escape, not even light. And this is why black holes are black, basically. But of course, there are deeper reasons which actually deals with the causal structure of space-time. Okay, enough for black holes, we know what they are. Let's now talk about the sonic ones, alright? So, why are they even proposed? Actually, they're proposed to make some lab studies of actual black hole effects, which we cannot study directly. But, well, how can we do? We want to study sound into a black hole, a sound black hole, a sonic black hole. But of course, if we're dealing with sound, we must have a medium for the sound to propagate. So we must set up our medium, and we're going to talk about the fluid, which has 3 hypotheses. It is inviscid, it is barotropic, and very, very important, it's locally irrotational, so that we can write our velocity field as a gradient of a potential, alright? This is very, very important because we can characterize our fluid in terms of these 3 dynamical quantities, the density, the pressure, and this very special field. What we do, we linearize our solution, our 3 dynamical variables, within a background, which we know, it's just background, and a little perturbation right here, which is in first order a perturbation. What we do then, we linearize all the equations which rule our fluid dynamics, which is basically Euler and continuity equations, and after lots of mass, which I can show you later on, we arrive at a wave equation, which can, after some manipulation as well, be written like this, in a quite compact form. The really amazing thing is that when we introduce this little guy here, a 2 tensor, it has 2 components, we may make some analogy and identify this with a metric. The same metric which characterizes geometry of space-time in our knowledge here, but it will now characterize the geometry of our fluid. So that's why it's a custom metric. It's as if for our fluid, for our sound itself, the fluid has a specific geometry. And just like space-time, it may be curved. And this is the general solution, which depends on the density of the fluid and the velocity mainly. Alright, so now let's actually analyze an actual metric. What can we actually see? This is our analog, which the analogy it seeks is the Kerr space-time, which is actually a space-time which rotates. Your mass distribution, it's rotating in space-time. Our analogy, of course, will be on fluid. It won't be 3D, but it's actually a surface flow. But of course, although it rotates, it's locally rotational because, well, vorticity is only locally defined, so we can actually, our theory still holds. Now, what we must do to actually have our geometry here is to solve for our velocity. We want our velocity field. So what we do is to solve this and use all our fluid equations to actually solve for the components, the radial and the tangential and the angular component of our field. lots of mass we can discuss earlier. We have this field here as our velocity, which you see, these are these two very important parameters and an inverse proportion to the radius. Alright? So now what do? We can substitute our velocity in our standard metric, and what we have is this, with these parameters really important here. What we do, we make a coordinate transformation only to make our metric really look like the Kerr one, which is in this form with temporal and radial actually separated and not together right here. Well, what this allows us to do is to actually look at our metric and seek for the same horizons, the same infinities. If you look here, if we have R exactly like C1 over C squared, we have an infinity here. This describes our horizon in this metric. Great. But also we have a 0 here, which actually describes something a little more different, which is our error region, which we'll describe right now what is. An error region is a region, in which the modulus of your velocity is greater than the speed of sound, in this case. But it's different from the event horizon, in which it's a surface which the radial component of your velocity is greater than the speed of sound. This will become important, this will become clear later on. But now, okay, we want to actually do something with this. What we're going to do, we are going to calculate how sound moves in our geometry, how sounds move in this fluid with this given geometry. What we do, we calculate the node geodesics, because sound is like light in our analogy. What we do, Lagrangian stuff, we have conserved quantities, and we can solve after some maths for we have the equations on motion of our fluid, of our sound moving through this geometry. What we did, we actually simulated this, so we have here our equation of motions. We fixed some parameters to just choose units and make everything more controlled. We want to see the behavior. We vary the C2 value, like this one here, and we vary the initial angle of shooting. So we have now here some simulations. We can understand it more, but this is just a plot of the XY plane of the fluid geometry. Okay, this I show later on. Very important, we can discuss. I'll just pass fast because there's a little more to talk about. Alright, so now, what about experiments? We did show you some simulation. Why don't we make experiments? Because, well, it's really technically difficult. We must make a flow supersonic while keep this flow laminar, avoiding turbulence and avoiding major perturbations which can supersede our sound perturbation. So this is really technically difficult to do. At least it's difficult, if not impossible for this model. So now I'm going to discuss the last point about Hawking radiation. Is it possible in our model? Well, what is Hawking radiation? It emerges when you try to combine quantum mechanics and general relativity, and let's try to use both theories at the same time. And well, what it predicts is that the particle excitations near the horizon, there is some the creation of a pair anti-pair particle. Some of them really near the horizon. One of them goes inside, it cannot escape. The other one must go out. And well, it's actually at first a virtual particle. As it becomes a real one, because the other one goes inside the black hole and it cannot escape, it actually emits. The net result is a thermal distribution of particles which are emitted from the horizon. You see here, this is the temperature, the order of magnitude for normal black holes, 10 to the minus 9 Kelvin. And we don't have a black hole in our solar system, so how could we even detect this? So this is why these models are proposed, to actually make some analogies in order to detect these effects, alright? So, can we do this? Well, if we have infinite resources and infinite time, sure. But of course, to do this, we must have a very, very controlled environment. So it has been done in 2016 by a major super researcher in a great lab, and he used a Bose-Einstein condensate, which is, well, it's basically a one-dimensional flow. In some part of the flow, he makes it supersonic. So this is his horizon, basically it's that. But, well, if we have a very controlled environment, we have a Bose-Einstein condensate, the fluid is very specific, he could actually detect this kind of temperature. The quantum pieces of sound were detected near the horizon, which actually mimics the Hawking radiation. Okay, so a sonic horizon was observed. Theoretically, the model is the same. Experimentally, well, we actually cannot do. This is just a summary of what I've discussed. And well, of course, we must talk about limitations, perhaps in the discussion. Let's think of it. What are the limitations? Is this model even right? I mean, we're dealing with a fluid and telling it behaves like a black hole, really? So hopefully we can discuss on these topics, and these are my references. And if you want some math to justify what I just said because I didn't have time, please be welcome to answer. Thank you. 2 questions.
Good afternoon everyone, my name is once more Anastasia Chervinska, and today I would like to oppose the very interesting, and I think, the task, the sonic black hole. At first, let's remind the task. We should create our own black hole for the sound, and describe some parameters which characterize the black holes for it, like as the event horizon, the Hawking radiation, and the properties of usual black holes, which can be correlated with the acoustics. Next. So the reporter gave us a good theoretical review. He wrote some equations for the general relativity and explained the black holes in the Einstein equations, but he gave us nothing in this point from himself. Then he described the sonic black holes and their usual properties, and as I think he made a very important thing, he described the restrictions which should be made for fluids to make sonic black holes. The liquid should be the viscosity of the viscous shouldn't be, the liquid should be viscous, and I think it's very important in this case. Then the reporter told us about the draining black holes, and I think that this may be explained more qualitatively but not quantitatively, because the concept is quite simple. We can discuss it in the discussion, the concept of draining black holes.
Okay.
And he explained the black hole for sound because it appears because of the vortices. And then he made the simulation for the sonic black hole for the draining black hole in his own situation, but for ideal liquid.
Nice.
Then the reporter. So let's come to the review of advantages and the drawbacks. The reporter made it, I think, quite good, represented us quite good literature review, and made the relation between the gravitational and acoustical quotients. I think it's quite important and quite nice. The report was full of mathematics. Then he gave us once more concept of the two concepts of black holes for sound due to rotation and due to the supersonic flow. And then the reporter defined the event horizon in his situation for the and made some comments about the Hawking radiation, which was asked for us in the task. And he made the simulation, and it's really good because it wasn't done by anyone, and it's really nice. But I think that there is some misunderstanding with the reporter, with the concept of this task, maybe as I understand it, because in my opinion, the concept of this task is to try to create the black hole. In the real life, there are a lot of restrictions for fluids. And the main of them is that the fluid isn't ideal at all. All real fluids really have viscosities. And really, some experimental simulation of sonic black holes were made experimentally, but they were made for Bose condensate. And what I wanted to report maybe to suggest something which may be realistic for us to realize in our lab. Maybe to create the black hole experimentally and by his own, or make some suggestions for it, to propose something which can be realized experimentally, more specifically. So now I think that I finished and we can come to the discussion.
Alright, so let's go. When I saw this problem, I was fascinated. I really wanted to give a very good work on it. And then I worked a lot. I really tried. I really tried some different setups. And then I studied, and I really became to the conclusion that it's really not possible to make with our resources an actual experiment of the sonic black hole. In fact, actually, and then I start thinking, and this problem specifically said, create your own black hole. So, like status speaker, like in many other experiments, we have build, you have construct. So, well, we created, theoretically, we simulated that, and like, well, experiments and simulations, like, there's something in this competition that like sideways, and so, well, it's just because it's theoretical, it's not in the real world.
Okay, I understand you.
Yeah?
I've dealt with similar difficulties, but I think that maybe you have some specific suggestions. What can we do to restrict the viscosity, the influence of the viscosity of the fluid? As I understand, I agree with me that the viscosity of the fluid is the main parameter which restricts for us the possibility to create our own black hole.
Yeah, sure. The problem actually is that, as I made here, I guess, we have to make our flow really supersonic, otherwise we won't have our horizons whatsoever. So the problem is, we must accelerate our flow somehow, but we cannot disturb the flow very much. We can't have disturbances because our sound is actually a tiny first order perturbation in our actual flow. So this is the difficulty, and I really couldn't find a way. So if you could, please tell us any ideas. I would be very grateful because I really couldn't make my mind on it. What I can say is that with limited resources, if I don't have a Bose-Einstein condensate, really I can't.
I understand you, and please can you tell me what are the problems with why are the supersonicness is so important for us? If the velocity will be, for example, 2 Mach numbers or 3 Mach numbers, which can be really created in our experimental conditions, what will happen?
Well, if it's Mach, it's supersonic, so it's alright. The problem is to get why supersonic important. Well, it's really important.
I understand why it is important, but
we must create our horizon, and that's what defines our horizon.
And what is the minimal Mach number for us to create a black hole? Is it 1?
It depends. It depends on the fluid or about what you are talking. The minimal Mach number you must have is 1. But
in real situation,
you must be careful because we are defining 2 regions on our sonic black hole: an ergo region and an event horizon. In an ergo region, we have the modulus of the velocity of the fluid flow
and
greater or equal to the speed of sound.
Okay, I understand you. And what is the influence of perturbations? Why it is so important for us to not have the perturbations at all?
Because sound is a perturbation, it's really tiny. If you have big perturbations, so sound's gone. This is the major role. Alright, so could we please try to speak a little bit about our actual creation, which is the simulation?
Of course. I wish to come to simulation.
Yeah, great.
Okay, and please, can you tell me what are the final results of your simulation?
Awesome, great. So important thing here, we're sending our sound particles, our sound, with 0 angular momentum. So, well, what would you imagine with something which is strong with no angular momentum? Well, it will go straight. It's radial motion, right? It has no angular momentum. But look at the simulations. Look what we have. Okay, here, it's still straight, but look at this. And look at this. It's not radial at all. Isn't that interesting?
Yes,
Isn't it quite interesting?
Yes, of course.
So, alright, so why does it happen? I really was, whoa, interesting.
And why does it happen?
You have
Can
an
you
idea?
identify what is the right line?
I think that I can suggest, of course, we may consider the situation, the very simple quantitative situations, like a funeral. Yes.
A funeral.
A funeral.
A funeral. Oh,
yes.
okay, yeah.
And we can see that it may be maybe the motion is the funnel-like, and here in your situation we have the draining black hole, as I understand it. Its concept is very like the motion the motion of fluid in the funnel. And of course, it's very relevant that you've got these results. I think that's very good. But what are the parameters of the what are the concrete parameters of this simulation? In what situation you have the straight line, and in what situation you have such a spiral?
Yeah, that's really. Can we?
Very quick response.
Okay, very quick. We really can't. We have here the parameters. It's like from here we can see this, but well, I should have some. I have to show some math, so perhaps afterwards, right? Some maths. Yeah. Or.
Okay, so I'm Piotr Storzenko, I represent University of Warsaw, and I would like to make review of this conversation. So, what everyone presented. First of all, Juan? Yeah, sorry, what's your, Andre?
Andre Juan, yeah.
Andre Juan, okay, he presented his idea of sonic black holes. We rejected permanently this idea, and we can't any ideas how to do this. So we were really glad that someone presented to us the solution, and it was really nice. Briefly speaking, he said about general relativity black holes, the reviation of the sonic black hole analogy. He showed us simulations, and I would like to reflect here for a moment that that for me, simulation, and if you have some, if you get something from simulation, it's as good as a normal experiment. Almost, it's really an experiment in for example, complex physics systems. Simulation is an experiment, so I don't see why someone is saying that it's not there was no experiment. And he also proposed some experimental possibilities. He told us something about Hawking radiation, showed us reference, and I must say that that you're really super fascinated about the problem, and I really like it. And why I asked to put slide by slide, it wasn't it wasn't the thing that it was so quick, but I was so amazed but your talk that I wasn't able to write notes during it. Yeah, so Russia basically liked the presentation. But they asked for a viscosity and how it can influence the model, because Andre told about lithium helium that is I think that doesn't have any viscosity, and we can discuss about later. And they were really didn't like the lack of experimental experiments, because there were only experimental setups proposed, as I understood. Yeah, Anastasia? Okay. So the discussion went something like that. Brazil said that it's not possible. It is not possible to make actually black hole in a real world. Russia stated this viscosity fluid problem of this. So Brazil asked for any ideas. For how to do it, how to do that. Unfortunately, Russia asked for a supersonic effect and didn't reflect on ideas, and then discussion went a bit wild. So now, when 3 minutes ended, I would like to ask one more time, Russia, what is your idea to this problem? And suppose that you have everything that you can occur in the world.
Exactly.
How could you do this?
Nice.
What is your idea for this? Because you asked Brazil for, it looked like you had some ideas, I think, like you disagree with them or something. It looked like that.
Okay, I understand you. So, as I understood the problem, is that how to compete the problems of real world when trying to create the black hole for sound.
How you do it?
I haven't done this, but
some ideas maybe.
That is, if I had anything which is in the world, of course I'll take the Bose condensate or the superfluid, and of course I'll take this. But I'll suggest maybe to, but I think that it's, but the problem of the Bose condensate and the role of the ideality of fluid can be maybe played with the liquid
Nitrogen.
Yes, liquid nitrogen. Sorry, I'm sorry.
Okay. So
And this
do
is
you
very.
think about this liquid nitrogen to do this?
I really don't think so. Not at least in the regimes we often have it.
And what would be the limiting factor for the liquid nitrogen? What do you think?
It's too viscous. It's really not applicable to our model.
Okay.
Of course, you could suggest, try to build a sonic black hole for a viscous fluid. Well, we have to deal with Navier-Stokes. You guys know what it looks like.
After this,
Sorry, I have a comment. I think
Please.
that if the experiment isn't suggested for a model, it's the problem of the model, not the experiment. And maybe you can have the certain region, the certain range of frequencies for which the model would work. The certain range of the wavelength for which your model could work.
Okay, so have you considered that idea that maybe we have sonic black hole, but only for a
Certain frequencies.
something? Like
Okay, but in which aspect are you saying that we have to consider wavelength? Super radiance?
I think that the
actual
idea was
phenomenon?
that, for example, if you put the wave with some length, the sonic black hole like completely like this wave.
Okay. So, well, we have to be careful with wavelengths because, well, this ultimately will determine somehow the size of our perturbation.
Yes,
so, of course, we must be
So if the
short.
perturbation
It must be. It must be little.
Yes, I think there is the clear correlation between the minimal size of perturbation and the wavelength.
Okay, and why do you think so?
I think that's quite evident because, for example, what gives us the perturbations? They gives us small vortices. Yes,
What is?
small vortices. Yes.
Vortices.
Vortices. No, they don't make vortices. It's like really acoustic perturbations sound,
Yes.
which the main thing we must avoid some vortices so that these perturbations are not masked.
If
This
you
is
are
the point.
interested in measuring an acoustic aspect, you must don't have perturbations on your system.
Exactly. Of course, there are some
Okay.
other.
Okay.
Okay, it's great.
I would
I
like
think
to
it's-
ask now
it's okay.
and invite the rest of the people here to discuss what properties of usual black holes wasn't represented in your model. And as I understood this, it's your black hole, your simulation of black hole. What was represented there and what wasn't?
First of all, eternal black holes.
Sorry?
Yeah.
Eternal black holes. In the lab, we can't make an eternal black hole. It's the first aspect you can't reproduce.
No, I mean that like when you compare the black hole somewhere in our galaxy in the middle and compare to your simulation, not to some laboratory experiment, but to your simulation. So what from because that's your experiment, yes. So what aspects of the space?
You mean like fundamental aspects, like actual black holes? They deal with gravity, with causality,
with the question for that.
Yeah,
so
exactly. So we must make clear that this is only analog, and that's actually must be explored in order to actually see, well, how much does the analogy valid, and how much does it work. So of course, an actual general relativistic black hole, it deals with space-time, with causality. We don't have these kind of effects here.
The opponent has mentioned that it's necessary to use a Bose-Einstein condensate to recreate a black hole. So, what is your opinion? Why is it important to use a Bose-Einstein condensate to recreat a sonic black hole?
I'm sorry. What?
Because you said that you would use Bose-Einstein condensate. So why would you use this to simulate or make the black hole?
This liquid is the most likely to the ideal as we can detect. So it almost doesn't have
so that's because it's the perfect liquid, yes?
It's a perfect liquid, yes.
Okay, and what's the opinion of your...
It's liquid really used for this.
Okay. Yeah, well, actually, even Andre presented some work from the other guy. Okay, and...
Yes, I have a question because you wanted to accelerate the fluid in your black hole to a speed higher than the speed of the sound in the water, yes?
in my fluid? Is it higher?
Yes, you want to explore the water to the speed higher than the speed of the...
Oh yeah, it must be a supersonic flow, yeah.
Yes, but there are other kind of wave that can flow in the water, like if you put the finger ripple, the small ripple.
Yeah,
moving
grab
slow.
the waves.
Sure. There's...
So why do you didn't, so if you wanted to study those ripples on the water, you wouldn't have to accelerate water to the...
Yeah, great, but that's nothing to do with sound. That's the point. There are many analogs. There are like superficial waves. There's some really great effects that you can make analogies with, but there's nothing to do with sound, nothing to do with our model, okay? Our sound metric, this actual correspondence between the theories, only work for sound perturbations, all right? These kind of waves are just way too much.
Okay, so, sorry, no.
These can be done.
You will talk. Like,
Yeah.
I would like to reflect on a problem statement.
All right.
I didn't catch what was the Hawking radiation occurring in your black hole simulation.
Oh no, we did not. It can be done. We did not look at this aspect, but yes, the model is sufficiently general for this. In our simulation specifically, no, because we focus in another aspect which was not explored. All right.
Sure.
I would like to discuss this if you have time. Okay, but all right. Sure thing.
Yes.
I'd like to come to this question because I think that we haven't discussed it properly.
Okay.
To this.
Super radiance. Have you ever heard about super radiance?
No, the properties of usual black holes.
That's the property of a usual black hole.
And what
super radiance.
What other properties of usual black holes can be considered in this task?
Okay, when you have a curved black hole, which is a rotating black hole, alright, it has angular momentum. There's an effect called super radiance in which some waves, some kind of perturbation in space-time, they pass not to the horizon, but in the ergosphere, and they kind of steal some of the black hole's angular momentum. That cannot be observed here because the kind of perturbations we're dealing with do not work like this. Surface waves, that could be done. Sound, no way.
Okay.
Right?
What you want to ask? Because you were going out of question, maybe you summarize.
I have the last question. If the flow is supersonic but there is no rotation, what will be the difference?
Okay, it can be done like in the Bose-Einstein condensate. It was no rotation.
What's the difference? You think?
Well, the dimension basically, you have to change your metric. Of course, it's not the same analog. It would be the Kerr metric. Like in the Bose-Einstein condensate, it was in one-dimensional flow. So no rotation, not locally never, but not like this kind of vortex-ish motion. So you have to change the metric, but the basic idea is the same. The model still holds.
If I could summarize everything.
So the time is actually up.
Yeah. So if you would able to one more time.
The time is up, so we should move on.
Okay. So
we move on to the concluding remarks.
So, alright, thank you very much for hearing my presentation. It is really a very, very interesting problem. Most probably one of the most difficult ones. I really worked very, very hard on it. I came to some conclusions which, well, we have our theory, really thankfully, we can create these kind of things with our minds. We can simulate that. We do not always have to go to experiments, and that's very good. So we couldn't, unfortunately, discuss what's the actual validity of our analogy. That's a very important issue. And well, if any of you guys want to discuss this with me, or the jury members as well, I'd love to discuss it, because this problem is really fascinating, and if we can further improve our solution to better understand the phenomenon, if you guys have any suggestion to actually make it, I'd love to hear. Right? So thank you for hearing, and well, nice. Thank you.
Then questions from the jury. Daniel?
I have a first question. The second might come later. For the open and first reported afterwards, you mentioned the importance of having a non-viscous fluid.
Yes.
But if I have a viscous fluid and I manage to have a flow at Mach 10, being laminar, why would this not create a black hole?
Because there would be I'm sorry, can I draw on the task?
do we need it?
Yeah, we don't need this. Reported, you want to give your perspective on the matter?
Yeah, sure, sure. First of all, we could have some kind of sonic black hole, definitely not the one I presented here. You could have some sonic, oh my gosh, okay, no problem. You could have some sonic horizon in which you have a viscous fluid, but perhaps the perfect analogy we presented here, like to having a metric and to perfectly define a horizon dealing with all the machinery of general relativity, which is differential geometry and all these kinds of things, really wouldn't be the same thing, okay? Structurally, it wouldn't be the same. But experimentally, if you have this, well, could be some kind of analogy, not the one we're looking at specifically here, but well.
I think that you can make the black hole, but the equations and the model that you use should be significantly different, because due to viscosity, there is the transition from the part of the flow with the high speed and to the part of the flow which hasn't any speed.
Okay, that's what you had.
Okay, so another jury question?
Do you know any analogy with surface, not sound, but surface waves to create a black hole?
Yeah, sure, sure. Actually, there is in University of Nottingham, we have a big laboratory which is called the Black Hole Laboratory. They have created like a pool, just like the one we showed here. It's like a pool, a tank with water, and you have a rotating like a sink, alright? And they make actual waves in the surface. And there they study some kinds of effects like superradiance and this kind of bigger effects. But like they study from 10 years, no, not 10, but like 2 years from now, I guess. And they have tried to do some stuff like with sonic black holes. In every paper they say, oh, we still are not there with water. And we can do this like sonic black hole. So there are some effects and there's really amazing things. It's really interesting. But well, with mechanical waves in the surface, sure. Not actually sonic.
Okay, you told us that you didn't do the analogy for the Hawking processes, but you said it's possible to do it?
Yeah, sure, sure.
Can you explain us first the Hawking phenomenon?
Yeah, sure.
What would the analogy be?
Sure, sure. The Hawking phenomenon, it's actually the thing we have from quantum mechanics. We have fields for every particle, and due to Heisenberg uncertainty principle, you may have some energy excitation which is really short, but it can happen when you create a pair of particle and antiparticle, which must annihilate because it really just takes energy for vacuum. But then, if it happens near the horizon, it may be the case in which a particle goes within the horizon and the other one, well, it goes out. It must take energy from somewhere,
Okay,
right?
So for the analogy.
Okay, now for the analogy. When we describe that perturbation, that psi, it is like a perturbation. We treated this like a classical field, right? And if we think of phonons, alright, phonons are the very important in condensed matter, which are like this emergent phenomenon, but we can actually be seen as the quantums of sound. So this kind of perturbations could be excited, and they actually happen for any kind of flow, yeah, because they are really happening all the way. It's just little perturbations which could exist in an actual fluid, and it's really in the model itself. We just have to establish the actual limits. We have to establish the metric, and then we could see it.
Would the phonon be the equivalent of the photon or the particle?
In this case, of the particle, because it would be like any particle in Hawking radiation. Hawking radiation is not only about photons. They go within the horizon, but well, not only photons. It could be like.
If you have a photon, you have an antiphonon with it.
Yeah, some kind of it. It must be a little cautious with this antiphonon because it's not like an actual particle. It's not like virtual. It's an analogy, but yes, some kind of it. Yeah, yeah, something like it.
Any other questions from the jury? Or should we give it to Daniel? Okay, then Daniel.
If we can come back to slide 8.
Sure. Me?
Yes.
Okay. Well, it's
just here.
Okay.
So on slide 8, you have the matrix that you use for the analogy, and you have this denominator, which is 1 over 1 minus r s divided by r squared.
Okay, just a second.
And on the Schwarzschild matrix metric that you presented, you don't have the square.
Oh, no, no, this is not Schwarzschild. This is for the actual metric with our vortex. It's, oh, where? So, here?
Like here?
Here?
Yeah, the radius in the denominator is squared.
Yeah, yeah, this is...
And in Schwarzschild, it's not squared.
Yeah, but it's not a Schwarzschild. Here it's Kerr. The analogy is the Kerr metric. The other one, for the rotating black hole, it has angular momentum.
Here is still linear in 1 over r.
I'm sorry?
I think here is still linear in 1 over r. It's not squared, I think.
Oh, you think it's not square here?
I think so.
Oh,
would this make a difference?
Yeah, well, if it's a typo, sure, but yeah, if you think so, probably sure it's a typo, it's wrong. But
I don't know, I'm just
okay, but
what
it's...
what you say is that it's because it's Kerr matrix, and Kerr matrix has this square. This is what you say, okay.
Sure, exactly. Not this exactly, it's the analogy, but we can take the horizons here.
Okay.
The horizon, the ergo region. Alright.
Small question. Can you
Please.
come back to slide 7, please?
Sure.
So you show us
Okay.
a velocity field
Sure.
with V r and V theta,
Yeah.
and then you say that V is ER over R at the end. The last
Here.
ER on the R, E theta on R, right?
Uh,
So if I take the divergence of this, it's not 0, right?
Yeah.
Divergence? No. No.
Is it a problem?
No, we must have, it must not be rotational, so we must take the rotational of it, the curl, like this one, and
What does dive 0 equal?
this
Times
one.
V correspond to?
Oh yeah, if it's a vector calculus identity, if we have a vector field which is like this, it's this operator here is 0,
Oh, okay.
we can
I
write
understand,
it.
I understand. I'm saying divergence of the field.
Okay,
It's not 0. It's a problem.
no, I don't think so. You have some flux over field, so not a problem.
Okay, thank you.